It's my distinct pleasure to welcome you here on behalf of the Institut Henri Poincaré. As probably all of you know, Henri Poincaré was the last mathematician to know it all and to contribute to about half of it. It's been terrific to actually have an office here for these 3 months or so. It was good compensation for the 2 years that we put into preparing this. So, well, the program is on the website, and I don't have a slide to show it here, but it's a very rich program. There are there's a lovely poster also. There are 4 courses of 2 to 3 weeks. 3 of these were followed or are being followed and will be followed by a 1-week workshop in the same area. There are 2 additional workshops, one of which, both of which have already occurred. One on linear response on climate, and another one on climate informatics that attached itself to this conference, and the third one that had to do with the kickoff of a European Union project, H2020 project on tipping points for the Earth system. So this is actually chronologically the, fourth workshop associated with this trimester or quarter, and there will be yet another one in December. So thank you very much, Alberto and Mark and whoever else, Omar, Gatas, who helped prepare this. And we're going to have a very nice reception, 24 floors high.
Be sure the elevator works, huh?
It doesn't work yet? Well, only people who can climb 24 floors and will have to eat all the food. Okay? With those things, and again, as Alberto said, you know, some of you here might have known Jean Golub from Stanford, leader in numerical analysis, particularly in algebra, but not only. He used to say there's no need to introduce the speaker. Obviously, all people are in the room because they know who he, she, or it is. You have to introduce the audience, but the audience here is so distinguished that I don't have to introduce it either. So, anyhow, with that, let's get down to business. I prefer to look at the same thing that you are looking at and try to point to it. So, you know, these days I get rather often to give the first or the last talk. Actually, Peter Jan had me a few years ago at the Lawrence Center give the last talk. So, you know, these are very cumbersome exercises because you can't just say what you want. You have to say what you have to say. So in any case, if any of the part that I want to say is of interest to you, there are some places where you can look it up. Let's get going. Data in meteorology and oceanography, basic ideas. Why does data assimilation work in geophysical fluid dynamics? It does, so many people don't worry, but I'll try to convince you that it is actually an important question for mathematicians. Novel areas of application, I'm only going to have 1 slide each for 2 of these because I only get 25 minutes to talk, and then you get to ask questions, concluding remarks, and I have 3 pages of bibliography that you'll have to probably ask me for because I won't have the time to show them to you unless you do. Okay, so what are the main issues? Actually, in particular, in France, where you know, Albert Tarantola was a great influence on data science and the geosciences, and of course also in the United States, where Backus and Gilbert were, there existed quite a practice of inverse problems in solid Earth, but The solid Earth stays put to be observed, at least on certain time scales, not when it shakes, when it doesn't stay put at all, but the atmosphere, the oceans, and many other things do not. They do move. There are two types of information: direct observations and indirect dynamics from past observations. Now, there is no compensating for that. There's a lot of talk of big data today and just replacing everything we've been doing by computers, okay? But I think that this source of information is important. We can get everything that's good from big data and machine learning, but not renounce the passion of the dynamics. Okay, combine the two in an optimal way or in optimal ways. Advanced data assimilation methods provide such ways in sequential estimation, Kalman filter, and various modifications thereof, and more recently particle filters and control theory for the variational adjoint methods. The two types of methods are essentially equivalent for simple linear systems, a so-called duality principle, but their performances differ for large nonlinear systems in accuracy and computational efficiency. So the name of the game, at least in as far as applying data assimilation to the biggest models we have for numerical weather prediction and for various purposes in oceanography, study optimal combinations of, as well as improvements over currently operational methods. And when I first wrote this slide, currently operational methods were things like optimal interpolation, but I've taken that out of this slide, okay? So data in meteorology and oceanography, so in situ and remotely sensed. So I can't resist to show you a little bit of the past, which I still live through. So this is from the preface to this book on dynamic meteorology data assimilation methods, which was the first book sort of commercially available outside the so-called GARP, Global Atmospheric Research Program, with these editors. And these were the systems in, that were put up by what was originally called, with a second order acronym, FIGI, the first GARP global experiment. But when it became clear that there wouldn't be a second one, it was rebaptized the Global Weather Experiment. So this is a count of all the different things, and the total number of observations was order of 10 to the 5 scalars per half a day to a day. So you had, with respect to the number of degrees of freedom in numerical weather prediction models at the time, order of 100 observations per significant degree of freedom times significant time interval. The delta t is not the time step of the model, it's the time that weather changes in an observable way, so it's a few hours. So this is an amazing result. You know, I always used to ask, why are we doing such a lousy job with so many data? Okay. Well, we're doing a better job. We have also 100 times more data nowadays, or 10 to the 7 observations, and many more degrees of freedom of interest too. In the ocean, the situation was much more deplorable because, as Walter Munk and Carl Wunsch observed in an important paper, water is not transparent to electromagnetic radiation like air. So these were so-called mechanical bathythermographs, and these were expendable bathythermographs, at the time a big improvement. So at the time, there were 10 to the 4 fewer oceanographic observations than meteorological observations by the same normalization. And of course, by now, things have much improved, but it is still the case that we can't see with the EM rays through water. So, you know, it's, here you have some of the first operational, well, experimental satellites for oceanography with altimetry, and there's a full coverage of the surface of the oceans, but certainly not three-dimensionally. Okay, basic ideas, data types and issues, how to combine data with models, transfer of information between variables and regions, filters and smoothers. So this is out of, again, a table that was provided by another contributor to this volume in 1981, Niels Gustafsson. And this is the sort of things that you had in 1981, so this is now almost 40 years ago. Okay, you had successive correction methods, some polynomial interpolation, you know, single variable, multivariable, etc. And that in the 80s came essentially the two approaches, sequential estimation and control theoretical methods that are, you know, still all the rage today. So, basic idea is, you know, there was a lovely course of 2 weeks that preceded this workshop, and Marc Bouquet talked about, you know, many things that are in his book with Ash and another co-author. So you see a lot of matrices and inverses of those matrices, which of course you should never actually compute, okay? You should only solve linear systems. But it's really simple. So we want to estimate the temperature of this room based on the readings of two thermometers, presumably independent, by a linear estimate, okay, with positive coefficients summing to 1, what's called a convex linear combination. The interpretation will be that one thermometer is a first guess of a numerical forecast model. The second thermometer is the actual observations, radiosondes, satellites, etc. And the estimate is a so-called objective analysis. I have a slide to show you why it is called objective analysis. So, okay, if the observation T1 and T2 are unbiased, and we want T hat to be unbiased, we have this. So, you know, one can write also T hat in an asymmetric way as updating, because remember that this is a first guess, and this is a so-called innovation vector. You know, the new information you get minus what you think the information ought to have been. So if T1 and T2 are uncorrelated and have known standard deviations, well, the first one is maybe true to some extent, the second one not quite. You define A1 and A2 as the standard deviation squared to the 1 over. So these are called the accuracies, okay? And then the minimum variance estimator is this. So this thing is all those matrices and their inverses that you see in the full glory of actually doing data assimilation. That's all it is, and the accuracy is clearly larger than the better of the accuracies of the two thermometers. Okay? So that's blue. And this is, again, in the sequential estimation approach, you know, the true evolution given by that damn dynamical operator that we don't want to renounce. You know, we will not renounce the devil of the dynamics, okay? And these are the observations. And at the time when that slide was first done, the model was necessarily deterministic. Now we can also have stochastic components. And then you combine these two in the probabilistic update. Now, one important thing that distinguishes what we do from what is done in many other areas, in particular what was done in engineering applications of Kalman filtering, is that we actually have partial differential equations rather than ordinary differential equations. And so an important ingredient is the advection of information. So again, this is one of the many papers that was written after this global weather experiment was carried out to illustrate the importance of satellites. It shows essentially the field of the 6-hour forecast with minus conventional in the no-sat case and with a Figge analysis here. I said Figge became GWE, which is less pronounceable. And the point is that if you didn't have satellites, the errors over the oceans are quite large, and that over 6 times, a lot of this ignorance in this case is advected over the western part of the Americas. The satellites wipe out this ignorance and they wipe over the oceans, and therefore they also wipe out ignorance over land. Okay? So the advection of information is very important in the same way that what was known, the exchange of information between variables in ODEs as well as in PDEs. So again, going back to Norbert Wiener, there are essentially 4 products of estimation. So you have observations here, green spots between T0 and T1. So if you estimate at the end of the interval, that's filtering, okay? Then there is smoothing if you estimate everywhere here, full-length movies, prediction, estimating past the observations, and an important result of the theory is that you can do no better than estimating from the observations, doing filtering, obtaining this initial state for the latter forecast. That is obvious after the fact, but not necessarily before. Okay? So this is the general picture that has changed from Norbert Wiener. Okay, and then there's parameter estimations, and data, I'm going to tell you on one slide what that is. That is applying data assimilation to detection and attribution of climate change. Okay, so all these need different combinations of those matrices and their inverses. Okay, now why does data assimilation work in geophysical fluid dynamics? Well, first of all, geostrophic adjustment. So here's a little history. This is a well-known paper written by Czarny, Fjotov, and von Neumann, when von Neumann convened that famous group at the Institute for Advanced Studies and gave them the ENIAC to play with. So it became obvious. This paper was published in 1950. Already in 1941, another person in that group, Hans Panofsky, wrote a paper called Objective Weather Map Analysis. Why objective? Because he says in the paper, okay, that you used to just draw contours, isopleth, by hand from the observations, and that had various disadvantages, but in any case, he wanted to, okay, instead of subjectively drawing isopleths and approximating the derivatives by ratios of finite differences, to do this in an objective way, and this is the abstract of the paper. I won't dwell on it. So basically, starting with a so-called Joint Numerical Weather Prediction Unit in the 1960s, led by Air Force Colonel Phil Thompson, and until the weather satellites came up in the late 60s, and objective analysis were only done every noon and midnight Greenwich. And then there was also a paper actually a year earlier written at the GFDL, but this is much briefer and clearer and much more widely cited. Jules Charney with Milt Halen and Bob Jastrow at basically it's a Goddard Institute for Space Studies, had the idea of using incomplete historical data to infer the present state of the atmosphere. Okay? And this is one of the principal objectives of GARP is the acquisition of data which define the synoptic state, in other words, the instantaneous state at those synoptic times, noon and midnight, the atmosphere globally for use in long-range prediction. Since all proposed global sounding systems suffer limitations, the concept has arisen of a combination of several such systems permitting trade-offs among the meteorological parameters and between space and time. So there is a sentence on the next page. If it should prove to be possible to obtain the large-scale wind field from temperatures alone, which was what the satellites gave at the time, the timetable for the implementation of GARP might be substantially advanced. So while I was actually a postdoc at the Goddard Institute for Space Studies off the Columbia campus, There was a group of 15 people that I led, and 2 of those were authors of this paper that eventually came out of it in 1979. So this was 10 years later, on time continuous assimilation of remote sounding data and its effect on weather forecasting. So again, the sentence up here, and what's written here is satellite sounding data, though promising, promote only one of the basic variables with temperature. By now we have winds and other things, but still, moreover, it's still, if for the atmosphere, mostly temperature, the mass field. Moreover, while the conventional data sets are available simultaneously over the entire globe, temperatures are obtained only in asynoptic time continuous fashion. So this is the real beginning of data assimilation, you know, the advent of satellites. So Charney put forward the conjecture that a complete knowledge of a continuous temperature history of the atmosphere will determine other initial state variables, in particular the winds. And so this is a paper the next year in which this, I'm just giving you the simplest illustration possible. So, you know, frankly, when I saw that sentence, being trained in engineering, in engineering fluid dynamics, I said, baloney. That can't be true, okay? And it's only later that I learned and showed that it is true, and this essentially because of geostrophy. Because on large scales, the mass field history does determine the wind field. Okay, so in a rotating Cartesian coordinate system, the linear shallow water equations are this. You've seen them before. And so differentiating these 3 equations, this with respect to x, this with respect to y, this with respect to t, and substituting into the continuity equation, you get this relationship, which contains only spatial derivatives of u and v and time derivatives of the geopotential. This equation, together with the continuity equation above, can be written as a Cauchy-Riemann system for the velocity components below. And we also did work on how to solve this in various nonlinear situations. You get a Monge-Ampère equation of mixed type, and well, anyhow. So similar diagnostic relations for the velocities were obtained for nonlinear shallow water equations and baroclinic models, and Edris Titi here and colleagues obtained recently other rigorous and more general results. Okay, now, stability. This is out of a paper by Alberto and myself and Anna Trevisan, who's no longer with us, and Francesco Boldi in Chaos. And it just shows that an assimilation experiment with a 40-variable Lorentz model, well, for which the spectrum of Lyapunov exponents is this, so this is 0, there are a few positive ones, is pushed below by applying this idea of ANAS, of assimilation in the unstable subspace. But, and I can't tell you more about that, if the atmosphere were linear, there would be nothing that you could do about what happens in the unstable subspace. Okay? You would get still compression in the stable subspace, but not in the unstable one. So nonlinearity is of the essence. Novel areas of application, I'm going to make it, Alberto. Okay, detection and attribution. So, you know, observed forcing natural anthropogenic, observed system behavior, temperature, precip, trends plus events, etc. Evidence of causal links. There's a whole literature on that. And applying data assimilation to the problem turned out to be a useful idea. And we have some papers on that. Another area of application is space physics data. So again, having lived exclusively and still with a leg over in an institution which has a lot of space plasmas, I can tell you that space physics was a little bit like oceanography when I got into it, thanks to Alan Robinson, who became curious about data assimilation. In other words, you know, in oceanography, basically, as I showed you on one of the slides, it was said that, you know, big men with big beards went out to sea and threw one of these manual bathythermographs overboard and hauled it back, and then went back to port and wrote 10 papers. And so space physics used to be like that. You know, you work half your life to send up an instrument in a satellite, then that takes some measurements, and then you spend the second half of your life writing papers about that instrument. So now you have constellations of instruments, and there's interesting stuff going on. This is out of one paper of Dimitri, I gather, can't be joining us, and Yuri Spritz, who's now a professor in Potsdam, and Richard Thorne, who was Spritz's thesis advisor, and it has to do with Van Allen radiation belts, and you are trying to determine this index of solar activity, the external forcing, used to determine the position of the plasma pause, which you see here. So basically, it turns out that each time you apply data assimilation, whatever your favorite system is, sequential estimation, optimal control, or some combination of the two, you learn new stuff. In space plasma, the thing is that the density is exponentially decreasing. There are orders of magnitude in this coefficient. So we had the idea of introducing this log normal EKF, which even for a linear parabolic equation like the one that covers this density here becomes nonlinear, but you know how to do such things, okay? And paleoclimate, I think I'm going to go very, very quickly. So parameter estimation for energy balance models with memory. Okay, here's one of these energy balance models that governs this sort of thing. X is a meridional coordinate, and little t is time. And you introduce a delay into the albedo because it takes time to build an ice sheet. Okay, and so the application of this sort of thing to paleoclimate has a particular feature that not only don't you know exactly the dependent variable, but you don't know exactly the independent variable. In other words, the depth in the core is hard to translate into time. Okay? So you need to estimate both of those things. Okay? And it turns out that there's some pretty amazing results. I mean, typically, as I will say in one of the conclusion slides, you need much fewer observations than you would think. Okay, so I made it to the concluding remarks. Okay, computational advances, hardware, more computational power, CPU throughput, larger and faster memory, software, better numerical implementations of algorithms, automatic adjoints, various sparse matrix algorithms, better ensemble and particle filters, efficient parallelization. A problem that was with us since the preparation of GARP was, which was looked at through what was called OSSE's observing system simulation experiments, is how much hardware do you have to put up there in order to get the results you want? So how much data assimilation versus forecast? So, instead of doing the two separately, design integrated observing forecast assimilation systems. The truth of the matter is that space agencies tend typically to favor engineers over scientists. It's not the instruments you want, but the instruments you get. Okay? So this is a beautiful principle, but okay. So an important result is that you need no more independent observations than DOF to be tracked. And this is a series of very different papers that establish that in different ways. And still the cost, while advanced data assimilation is much more expensive than just a straightforward numerical weather prediction, it is still much less so than that of instruments and platforms. Well, this is a tongue-in-cheek. At best, use data assimilation instead of instruments and platforms, because you can't do that, especially since now the big computer companies won't let you do that, because they want you to use their big cloud and so on. At worst, use data assimilation to determine which instruments and platforms, in other words, advanced OSSEs. And then use any observations if forward modeling is possible, observing operator age, satellite images, 4D observations, pattern recognition observations, and in phase-space statistics, which is not done so much. Okay, theoretical concepts can play a useful role in devising better practical algorithms and vice versa. Judicious choices of observations and method can stabilize the forecast assimilation cycle, and then trade-off between cost of observations of data assimilation. At the time, there was even a question, because ocean data were so lousy, whether when you started doing coupled ocean atmosphere models, you should use ocean data at all, which is silly, of course, but it was a winning argument at least one workshop in Portland that I could not attend, okay? But that has changed, so now it's understood that the ocean data assimilation is a good thing, and you even have so-called reanalyses. They help estimate both ocean and coupling parameters, changing in estimated parameters, compensate for model imperfections. So that's another issue when you do parameter estimation. You might find out that the parameter that you think ought to be constant in time changes according to the state of the system. So that is one way of compensating. There are things like DART, the data assimilation research test bed. Aiming, I love this, aiming for better prediction. So this is, again, tongue-in-cheek. I don't have the time to unveil this to you, one line at a time. So, pre-data assimilation, fewer data, poor models, theoretician, science is truth, don't bother me with the facts. It used to be said, don't bother me with your lousy observations. The observer experimenter, don't ruin my beautiful data with your lousy model. Early DA, better data, so-so models. Stick it, in other words, the observations in, direct insertion, nudging. Advanced data assimilation, plenty of data, fine models. Second duality, various other things, and post-industrial DA, satellite images directly going into weather forecast and climate movies. As a matter of fact, one of my brothers-in-law who was trained as an engineer in France, once when we were hiking, revealed to me that he thought that that's the way that weather forecasts are done. You just look at it. So maybe he was right. So we've come a long way in 50 years, okay? Some advances are laborious and incremental, e.g. sequential versus control theoretical methods and combinations, but other fresh and exciting. Apology for not being excited by that part. The latter include new areas of application, biology, geomagnetism, paleoclimate, space physics, data, as well as novel methodological challenges, multi-scale and multi-model problems, inverse problems for evolution, including climate simulation and sensitivity studies and uncertainty quantification. Technological advances put new problems, massive data sets, higher resolution, and help solve them as well. Overall, it's a brave new world in which data and models actively speak to each other, and we do so to both. So enjoy this workshop and the rest of your career. This is from the New Yorker. Miss Peterson, may I go home? I can't assimilate any more data today. Thank you very much.
Maybe we have time for one quick question. Please.
When you were showing a slide with the Lyapunov exponent, sort of bringing the positive Lyapunov exponent below zero,
Yeah.
You made a comment which intrigued me, but I don't think I quite understood about how that would not be possible for a linear system.
Well, because in principle, thanks for asking this question, very crucial, because in principle, proofs exist for convergence of the Riccati equation, etc., in linear systems that are stable. And the fact that is numerically observed in these nonlinear systems, which were dealt with, the Lorentz 63 and the Lorentz 96, and then some other models that Alberto and Marc Bouquet and other people worked on, they are nonlinear. So my contention is that the difference, the Riccati equation is known by now for the covariance matrix, is known by now pretty well. So it's very hard to figure out something that people haven't thought about, and they haven't. So I have a little idea that we're exploring, some of us, that the nonlinearity has something to do with it. Okay? Thanks very much for the question, because it's one of the things that I really wanted to get through. So, I can show you some of the references. Okay, there are quite a few, there's a lot of stuff by now. Okay?
I think we have to move to the second speaker. Thanks again, Michael.